Okay. So yeah, it's 2:35. This is COMP2404, Introduction to Software Engineering. So we're here on the 29th. We started talking about exceptions last class. We'll continue that today and maybe get into the standard template library. Up till here, this is everything you need for assignment 4, of course. We don't do exceptions or even really use the standard template library in assignment 4. So as far as that goes, the official due date for now is next Wednesday. I am guessing we might hear more information by Friday about the strike and what might happen. Either it'll end or the university, I know they're talking right now about, what to do potentially if it goes on. So I'm hoping by this Friday we know more. If the strike does go on, then this due date might become flexible depending. That is, make sure you get your assignment done for that date. But if I don't have any TAs to mark it, then I'm going to set something up on Gradescope, at which point you'll have a few extra days to submit it. But don't count on that, right? Just so that you guys have some mark. It'll be a very coarse-grained mark and probably higher than you would have gotten, but at least I can test to make sure you wrote something that worked. That's all. So yeah, I don't know what's going on. Let's just stay flexible, I guess. Tutorial 10 is actually due. It's not due that weekend, it's due the following weekend. And if you want extra marks, the tutorial servers are open. Just submit your tutorials and you can get some extra marks that way. So yeah, questions? Yeah. Too late is literally Wednesday. So if on Wednesday I have TAs that will mark it, that's the due date. If I don't, then I'm going to set something else up. Again, just so you have some sort of coherent mark. The university might give us some guidance on what to do, but if not, that's the rough plan I have. Other questions? Okay, so last class we were talking about exceptions, or we started talking about basically different types of errors, and the difference between errors and exceptions, right? So, and essentially it boils down to errors are inline, something that you would expect that might go wrong, such as somebody passes in a bad value to your object. It's something that I can check for. Oh yeah, so as far as the mask goes, I am a little bit sick. I have a cold, it's not COVID. I took a test this morning. I don't actually feel that bad, but I'm very stuffed up. So, you might want to keep your distance. Anyway, inline error handling. So error handling is sort of minor stuff, checking, validating values that are passed into my object. Things basically that I can check with an if statement, right? And so these are small errors, they're expected some of the time, and we handle it with inline code. Basically, we have our application logic and we inject into that some if statement that tests an error condition. We do that with checking indexes in a collection class and things like that. So yeah, inline error handling is good for basic error checking, but we don't want to really have a lot of it, right? We don't want it to overwhelm our application logic. We want it to sort of be, a little bit of basic data sanitation. That's fine. Exception handling is for things that are more rare, writing to disk and all of a sudden I lose the disk drive breaks or I lose contact with the network. So these are less frequent, harder to predict, harder to check. And then what happens is also, the big deal with C++ and exceptions. I mean, you've used exceptions before, but it's really that memory management and closing off of resources. So, I mean, all of this is basically, this entire lecture is about the control flow and how it's affected by throwing an exception, and then how we handle things like dynamically allocated memory that now has to be deleted. What do we do? So that's basically the entire thing. We'll start by talking about the control flow of throwing an exception, and then we will get to possible problem areas. But if an exception is thrown, then you have some choices of what to do. You can allow execution to continue, right? If maybe you're certain that you've handled this exception and all of the consequences of it. You might notify the user that there is a problem. I don't know if I've seen that using Ubuntu, is saying, well, Ubuntu's reached an inconsistent state. If this happens again, you might want to shut down and start over. Right, and the idea behind that is, well, if you're not sure, if something went wrong, like your date variable is now the 13th month, then that's really sort of unexpected, and maybe you should crash at that point so that you do not perpetuate this error throughout the rest of your program. But that's up to you. Sometimes it's better to terminate in a controlled manner than allow some problem to become way worse. So when we throw an exception or exception handling in general, we separate the error reporting, so finding the problem, from the error handling, which in some cases is quite useful. Yeah, so error handling provides an alternate return structure. Again, useful in some cases, not so dangerous in other cases, I guess. So the normal program stack return method is bypassed, where we return from a function, we pop that stack frame off the function call stack. We bypass all of that when we throw an exception, or well, depending on how it is thrown. Okay, so the C++ library has an exception class. This is an abstract class. So it tends to be the base class of user-defined exception classes. So you just define an exception class for whatever you think is going to go wrong. There are a couple of concrete subclasses. One of them is runtime error. I forget what the other one is, but and essentially it takes a string message as an argument. So this is a message saying what went wrong, and then we call on the what function, and it returns that string. So that's the idea behind the exception class. But we'll see in C++, we don't have to just throw exceptions. We can throw all kinds of stuff. All right. So exception handling is, well, throwing and handling exceptions uses the try, throw, catch blocks, right? So that's pretty standard. So here we have an example. Inside the try block, we do some error checking. If we find an error, we report the error by throwing, well, in this case, we're throwing a constant character array. We can basically throw whatever we like. And then we handle the error in the catch block. Okay, so that's the basic structure. Nothing you haven't seen before, but we're going to look at what happens to our control flow when we throw exceptions, and then we're going to look at how to handle problems that happen because of it. Okay, so we have here a main function, and we have forward referenced 3 functions that don't really do anything except announce that we've been in there. So starting in main, we call func1. In func1, we say we're in func1, and then we call func2. In func2, we say we're in func2, then we call func3. Func3, we say we're in, then we exit and return back the call stack, right? So if we look at sort of what is happening, yeah, what is happening? Well, our main function is the bottom of our function call stack. Then we call func1, that goes up here, and we start running code in func1. That calls func2, so that's another stack frame. That should be func1. And then that calls func3. And that's the normal flow of control. And then when we return from func3, of course, that gets popped off, and then this gets popped off, we return to func1, that gets popped off, and we return to main. All right, so I mean, again, nothing spectacular at this point, but then we'll see how we can mess all of that up by throwing exceptions, right? So we call func1 from main, call func2 from func1, func3 from func2. We exit from func3, and then we return down the function call stack, where we basically announce where we are every step of the way. And then, so that is the normal flow of control. In our main function, we have a try catch block. So this func1 call is embedded in this try block. And so what we're going to do is right here, we will, at the top of our stack, we will throw a runtime error. We'll say error from func3. Okay. Now, maybe you notice this is a static declaration, which I can do. C++ is going to handle that for you. So generally speaking, you shouldn't statically allocate something in a function and then return a pointer to it. But if you return the thing itself, well, the compiler can figure it out, right? So it's basically not going to allocate space here. It's going to allocate space, possibly space down here. Okay, so let's see how that changes our control flow. Okay, so I go up the function calls, call func1 from main, call func2 from func1, func3 from func2. In func3, I throw this exception. This gets skipped. The compiler looks here for a catch block. It doesn't find it, so it pops that off the stack frame. This line of code gets skipped. This line of code gets skipped. Finally, in the main function, it finds that catch block and it prints out the error. So we said error from func3, and then it resumes control after the catch block, and it prints out this last line. Okay, so we skipped a lot of code there when we threw that exception. And that is not a problem in this example, but potentially a problem. But yeah, any questions? All right. So yeah, that is called stack unwinding. So here we had the normal flow of control when we returned from a function. It got popped off the stack. But here, if we throw an exception, well, then the compiler looks for a catch block in here. It doesn't find it. So this gets deleted, and all of your local variables, any information you have there, it's also gone. Okay, so that can potentially cause a problem. At which point it looks here and it says, I can't find it, so that's gone. So when you throw an exception, you better be sure that you want all of that state gone. You better be sure that you don't care if you exit prematurely from these functions, or if you do, that you've handled any resources that you have to deallocate. It looks here, it doesn't find a catch block. Finally, it looks here, it finds a catch block, and that's where it resumes. Okay. Yeah, we got P2. Okay, so let's take a look at another example and see again how the flow of control goes. So we have a main function and we have a divide by zero function. What the divide by zero function does is it takes a numerator, a denominator. It tries to divide the numerator by the denominator and put that into this result and return it. Here we throw an error. We don't catch it in this case, just to see if we throw an error and it's not caught, then what happens is enter two numbers, 3 and 4. Result is 0.75, which is great. If I enter a character, let's say, it's trying to read into an integer, then it's going to throw that exception, right? It's going to trip this flag on my cin object. It's going to throw this runtime error. This runtime error is not caught, so the program's just going to terminate, right? So everything's going to be popped off the stack frame, and then our program will crash, which is possibly not a bad thing. But so this is just a simple error check, basic input sanitation. I just threw that runtime error there. I could have handled it differently, but I threw a runtime error to demonstrate that it's going to crash at the point. But let's try and now, so this is a dangerous piece of code here, right? If I divide by 0, then that's an infinite loop, or, well, you'll probably get a compiler, a runtime error thrown. So what I want to do is I want to do some error checking. So this is a dangerous piece of code. I'm going to put it inside a try block. And then I'm going to catch some error message. And then I'll say, output that error message. And then I will resume this flow of control after the catch block. But I didn't really do any error checking here, so I'm going to actually check if dem equals 0, then I want to throw divide by 0 error. Okay, so I'm throwing a string. Well, I'm throwing a constant character array. So you'll notice that I'm also catching a constant character array. So in C++, one of the things you can do is you can throw and catch anything. In Java, I think you are restricted to, it's not exception, but it's the superclass of exception, whatever that is. I forget. But yeah, so you can't really throw an integer or a string in Java. Everything has to be an exception. But in C++, you throw whatever you want. You can throw a number. I could throw, in this case, a constant character array. Important to note, this is not a string. If I put string here, this would not get caught. Right? It's different. We'll come to that a little bit later. I'll talk about why. But yeah, so if the denominator is equal to 0, I'm going to throw this divide by 0 error. And what this does is now it's going to skip this dangerous piece of code. To be honest, I don't know what C++ does if you divide by 0. I'd have to check it out. I know it used to be this, this would lock up your computer way back before they automatically checked for stuff like that. But yeah. Okay, so did I save it? No. Okay, so two numbers, 2 and 3. The result is 2/3. Let's try that again. So 4 and 0. I got this divide by 0 error, and then it printed the result. All right, so let's look at the flow of control here. Yeah, we took some input. We passed this little test. Then we called on this line. This printed out result, and then it called this divide by 0 function. And the idea is whatever is returned by this divide by 0 function is then applied to this stream insertion operator. The divide by 0 function, instead of returning something, or actually, no, sorry. It gets to here, it throws this divide by 0 error, it skips this step. It's caught here, prints out the error before, right, before this gets printed out. Then we return the result. We do get 0 returned here. That is also printed out, and then we're done. Okay, so and there's nothing wrong with that. We skipped the dangerous piece of code. We got an error message, and we got a nonsense answer. But that's fine. Maybe that's the behavior that we wanted. But yeah, questions? Okay. At this point, instead of putting the try catch block here, I'm going to try something a little bit different. All right, so I'm still going to do some error checking here. And if I do get an error, I'm going to throw one. But now I'm going to put the catch block up here. So now this becomes the dangerous piece of code, right? It's the dangerous function call. Yeah. So now I have this dangerous piece of code in my try block, and I throw an error down here. So let's see. 4 and 0, divide by 0. Okay, well, oh, did I not save this? Yeah, that was a little unexpected. So 4 and 0. So the result is now divide by 0 error. So it calls this function from the try block. We get to here, it throws an error. It skips this piece of code, but it also skips this return. So we get back up here. It now says, well, this is now, it's coming back up the function call stack by way of an exception. So it ignores the rest of this statement and it simply pops into the catch block, runs the code that's there, prints out the error, and then exits the main function. So here we didn't get, when we put the try block up here, this piece of code did not execute, right? Whereas when we put it down below, it did. So these are just some of the considerations you have to think about when you're plotting out your try and your catch and your throws, what's going to be the result. But yeah, any questions? All right. Yeah. Yeah, there was one other, let me see here. We go back to 1. Actually, if we go to here, I have here a my class. I just made a class that takes a message and then I can print. So yeah, I can throw anything I want. I could throw my class, pass in the divide by 0 error. Did I input the, yeah. And then here, instead of catching a constant character array, I can just catch my class error. And then I can, yeah, that's no longer going to work, but I can call the print function on that. Right, so I can throw whatever I like, not just exceptions or, well, undefined reference. Did I not? Yeah, sorry, I have to link it. All right. Sorry, I have to link it. There we go. Okay. So 2 numbers, 4 and 0, and I still get that divide by 0 error. And this, I believe, is part of my constructor. Yeah. So I made a version of that class. Okay, so that just shows the flexibility of the try, throw, and catch in C++. Yeah, so to reiterate what we looked at in that example, we're just looking at the flow of control. We're not really judging one over the other. It's just a question of what you want. This little, if I try to input something into a variable that won't hold it, then this flag will be thrown and this will return false. Note is that we could throw whatever we like. We could throw integers, strings, what have you. And we're throwing local objects, right? Which is, you have to be careful about stuff like that, but C++ is going to handle it for us. It will figure out where to allocate the memory so that you don't get some inconsistent state. Usually it allocates it in the catch block. Yeah. I think depending on the version, there might be a move operator that's invoked. But again, that's really sort of deep C++, and it depends on what version you're using. But whatever we do, the processing continues after the catch block. So we throw an error, it's caught, and we pick up where we left off. But if we pop a bunch of stack frames off, those are gone. Okay, so try, throw, and catch. our try block contains our potentially dangerous code, whether it's directly dangerous or if it's, some dangerous piece of code contained within a function. So basically what we're saying is that something could go wrong here and we would like to handle that error. And yeah, it may not be there. It might be somewhere up the function call stack, but we've embedded it in this try block so that we can catch the error. So now the throw, while we're somewhere in our program and we've detected something that went wrong in some sort of semi-catastrophic way. So we're not prepared for it, so we in some sense pass the buck, right? We throw an exception, we say, well, I'm not sure how to handle this directly. I'm just a helper function, so you can figure it out. So we throw an exception or some kind of error. If we throw something and there is no try block somewhere up the call stack, or if the catch block does not catch what we're throwing, then the program will terminate. Okay. Finally, the catch block. This is the block that deals with the problem, right? It catches the exception and figures out what to do at that point. The catch block is always immediately with the try block, sort of like an if-else statement. The throw can be somewhere else, but the try block is always, or the catch block is always with the try block. All right, so yeah, this is just sort of the example that we looked at. Here we have a potentially piece of dangerous code, but we call a function, and this function throws the error, and then the error is handled back up in our func function. Okay, so when an exception is thrown, we transfer control to the catch block. If the catch block is down the stack, the function call stack, then all of the stack frames are popped off. So we're going to get to this and the consequences. However, one thing to keep in mind is sometimes you do want to pass the buck, right? You're just a helper function, something goes wrong, and you don't know how to handle it. So you throw an exception instead of trying to figure out, right? So when we handled, errors in our assignments, generally speaking, I wanted you to handle them as close to the control objects as possible, because the control objects sort of know the context, right? So they know if there's a console, they know if there's a view they can print the error to, but the functions that, or sorry, the classes that are down I guess the application tree, those are not, they don't know what's going on necessarily. They're just being used by the control object. So they don't know if there's a console to print to, right? You might try to print an error message to see out, but whatever, they're on a phone. There's no console to see. So your code might be a library for some other app. Basically, you don't always know how to handle errors. So you can pass the buck by throwing exceptions and let whoever is using your class figure that part out. And that's actually good software engineering. Yeah. Right. All right, so this is nothing we really haven't seen before, but I can have, my try is my dangerous code. It calls this middle, which is divide, then throws an error. And this is, we could think of this as the function call stack, right? We have func, we have middle, we have divide, and then we start looking for catch blocks. And if we don't find catch blocks, we simply pop those off until we come back to where we can handle the error. Okay. All right, so try catch in four loops. Take a look at that. No, sorry, this is something a little bit different. Okay. All right, so we have a main function here. We have a enter name and a check name function that we're not using at the moment. Let's just get rid of that. Okay, so in our main function, we initialize a string. We call the enter name function, and we use that to give some name a value. We print out that name and then we return. Our enter name function takes some input from the user. So I'm going to type in a name and then returns that string. So we're going to see here a similar problem to what we saw earlier. But first, let's just run it. All right. So enter a name. All right. So it just takes my name in, prints it out. Everything's good. So what we want to do here is we want to check to see if it's Timmy, because Timmy is always in crisis and Timmy might be in trouble. So we're going to see if the name is equal to Timmy. And then if it is, we're going to throw whatever, Timmy is trapped in the well. Okay, and this is now a potentially dangerous piece of code, so we're going to embed it in a try catch. And then we're simply going to print out that error, same as we did before. Okay. So now we have a potentially dangerous piece of code where Timmy might get into some trouble. So if I just put my name, everything works fine. If I put Timmy's name, it says Timmy is trapped in the well, but the rest of the code executes, right? So again, this is, sort of what we did before, but now there's more consequences to it. If I have the try catch block here, well, I simply throw this, I catch it here, I pick up where I left off, and I still return this string S. So this piece of code still gets executed. Some name gets, gets the name Timmy, and then I print out Timmy's name, and then I exit. Okay, so that's exactly what we would expect to have happen. On the other hand, if we do something like this, so now this is the dangerous piece of code. Okay, so we initialize the name here to abracadabra just for a placeholder. So it still works with me, but Timmy, he's always in trouble. Timmy's trapped in the well, but now this name variable never got initialized. So this is still abracadabra. So in my try block, I call this function. When this returns a value, then I execute this assignment. In this function, I throw this error. So then it abandons this piece of code altogether. It catches it here, and some name never gets initialized. Okay, so that's similar to the, when we did the return or divide by 0 example, but now I guess it's a little more in your face, the consequences that, if we structure our try catch block like this, then this little piece of code gets abandoned. If we put it further down, then it still gets run. But yeah, that's that. Yeah, questions? Okay. And then we could have a third function here called check name. Yeah, we could do something like this. And we can just say, if name is equal to Timmy, okay. This is basically functionally exactly what we had before. but now we just have a function call instead of checking directly here. But we still throw, and then it's still going to skip this return statement and still print out abracadabra. So Timmy is trapped in the well, abracadabra. So yeah, once we throw this, the compiler goes back to here. It says, well, there's no catch block, so I'm just going to abandon this function. And then it comes back to this one, the main function. There is a catch block, so it picks up here. Neither of these are right or wrong. It's just an example of some of the consequences of these types of design decisions. But yeah, nothing super complicated, but any questions? Yeah. Right. Yeah, basically, and well, that's a sort of a preview to these types of problems. So what if I allocated some dynamic memory here? Then how does that memory get cleaned up, right? So this, when I throw this, Timmy is trapped in the well, basically this line of all of the code that follows my check name function is abandoned, which could be some cleanup code, right? I could be calling delete on something that I allocated. And therein lies the problem. But yeah, other questions? Yeah. Yes. So there's a, yeah. So that is actually one of the solutions, is that you can have an intermediate catch block inside this function that does some cleanup if you need to. Yes. So that is one of the solutions that we're going to look at. So yeah, we're going to look at two solutions. That's one of them. The other is this resource allocation is initialization, which means that every time you dynamically allocate some memory, you tie that to the lifetime of a statically allocated object. And then once that statically allocated object goes out of scope, that memory is deleted. So that's a pretty good, and that's basically sort of what I've been trying to get you guys to do. Although on the assignments, the assignments are a little more complex than that, because we have these trees, right? So this object is responsible for this object, is responsible for this object, and so you can call the destructor all the way down the line. But yeah, that's the basic idea. Other questions? Okay. And we wanted to do, yeah. So here's another example of some of the consequences of try, throw, and catch. So here we have, well, we have our barnyard, right? We have a base class of animal. We have a bird, a chicken. These are all animals. A chicken is also a bird. A cat is an animal. A pig is an animal. And we're going to push them all on a vector of animal pointers. And then we can do the barnyard harmony where all of the animals sing. Okay. And then we're going to embed some try-catch in here and see what the consequences of that are. First, I want to go. Multiple catch blocks. Yes, that is another thing we're going to look at. You can have multiple catch blocks, and then the order is very important, right? So it's unfortunate that we, this comes so late in the class that we don't really use them in our programs, but they do make for good exam questions, eh? Because all of this is really just following the flow of control of your program. Nothing too complicated, but and make sure you're paying attention. All right, so if I look at my barnyard. All right, so our barnyard harmony, the chicken says cluck, cluck, the pig says oink, the cat says meow, bird says tweet, tweet, and then we exit after we delete everything. All right, so what we're going to do is, well, our pig doesn't really sing. Pigs can't sing, right? Everything else makes sense, but. So we'll throw a pigs can't sing error. All right, so now our for loop our barnyard harmony here becomes a dangerous piece of code. So we're going to embed that in a try catch block. Okay. So our entire for loop is in the try block, and then we catch it. So let's see what happens when we try our barnyard harmony now. Okay, so we start with the little red hen says her cluck cluck, and then we reach the pig, and the pig throws the error, and then it says pigs can't sing. So inside here, we have the error thrown, right? When we call the pig sing function, it throws this error. We abandon this try block, and we resume our control in the catch block. We print out our error, then we delete everybody, and then we leave the farm. So what happens is the barnyard harmony doesn't finish. All right, so and now that's, again, we're not passing judgment on whether this is right or wrong. This is just, maybe this is how you want things to go, or maybe not. But yeah, if I throw something in my try block, everything in the try block gets abandoned. If the entire for loop's in the try block, the entire for loop gets abandoned. So the other option for this is, well, maybe I take our for loop and I'm going to put it around the try catch block. Okay. Now I have one too many things here. And my indentations may be a little inconsistent, but you get the basic idea. So now my try catch block is completely embedded inside the for loop instead of vice versa. So now when I run this, so when Wilbur comes up to sing, Wilbur can't sing, but the rest of the barnyard harmony continues because, well, the error is thrown here. So when the error is thrown, we abandon this function, but we pick up here, and then we resume control after that catch block, which is still inside the for loop. So we keep looping. Yeah. So again, neither of these is right or wrong. It's a question of the consequences of what you want to have happen when you throw an error. But yeah, questions? Okay. Right. So yeah, whether we put the try catch block inside or outside of a for loop affects the behavior and the outcome of our program. In the one case, we abandon the for loop if it's inside the try catch block, or if the try catch block is in the for loop, then we simply continue. So, you know, these are things to make note of when you're designing or trying to implement exceptions in your code. All right, so somebody asked about multiple catch blocks. So when we throw something, there's only one parameter, right? We're throwing a single object or value. And once we throw it, the compiler looks for a catch block with the matching parameter. And we can have multiple catch blocks. They can all be together. They can be in separate functions, as we'll see. So in this example, they're all going to be together. If we want to make sure we catch everything, we can use this all-purpose catch block. The only problem is this will catch anything we throw, but we can't use the parameter, right? So we can't, because the compiler can't verify that you're going to be, it can't verify what this is going to be, so I can't, you know, I can't use it. So yeah, let's look at example 5. All right, so we have still our barnyard. Now these are very simple classes. I just really want the hierarchy, that's it. Yeah, just to make sure we understand the hierarchy. We have our animal base class. we have a bird, and we have a cat, I believe, and a pig. And then we have a chicken, which is a derived class of bird. And I think that's all we have. We definitely have at least that. And this is the hierarchy, right? So a chicken is a bird, which is an animal. A cat is an animal. Pig is an animal. Neither of them are birds. So this is what our class hierarchy looks like. So now, yeah, that's right. So we're going to declare a bunch of these. We're going to ask the user what they want to throw. We're going to throw some animals here. And then we're going to have this try block, which checks to see what choice the user made, right? If we select bird, if we type bird, it's going to throw a bird. I'm going to come back to this statement in a second. If we select chicken, it throws the red hen. If we select the cat, we throw Lily. If we select the pig, we throw Wilbur. And then else we throw whatever. Okay, so this is all within my try block. And then following that is multiple catch blocks, right? So we catch a chicken. If we catch a chicken, we just say that we caught a chicken. If we catch a bird, we say that we caught a bird. If we catch a cat, we say we caught a cat. Pig, we say we caught a pig. We skipped animal. Or we can catch anything, right? So if we don't know what we threw, we catch everything here. So yeah, let's make a run of that. What are we, P5? Oh, sorry, it's just P5. Yeah. Okay, select my activity. I'll say bird. It says bird alert. Fantastic. If we try that again, I'll say chicken. It says chicken alert. Great. If I say walrus, it says something. So walrus doesn't show up, so it just throws whatever, and that catches in the catch-all. So yeah, we can have multiple catch blocks. The compiler starts looking, and we have a note here that says the order is important. So the compiler starts looking at the top and works its way down, right? So as soon as it finds something that matches, it runs that piece of code and it skips the rest. All right, so what happens? It says order is important. So let's take the bird. We're going to put the bird above the chicken. So now what is the consequences of this decision? So what happens now when we throw a bird? What happens when we throw a chicken? Yeah, so we're going to catch a bird both times because a chicken is a bird, right? If we look at our class hierarchy again. So the order of these catch blocks is really important. The compiler doesn't go looking for the best one. It goes looking for the first one that matches. So if we try that again, we'll notice something. It gave us a warning. All right, it doesn't give us an error, but it says that my chicken's going to be caught by the earlier handle bird. Right? So it does recognize this, but it says, well, I don't know, maybe you know better than me that this somehow makes sense. So again, we could throw a bird, we get a bird alert. We throw a chicken, we get a bird alert. So now the chicken alert is completely useless. It will never get caught there. So yeah, we have to be careful of that. Not super complicated, but again, great exam question. But yeah, questions? Okay. One thing to note, so we threw a bird here, right? So these guys, we statically allocated some animals. That's fine. And here we just made a statically allocated bird and threw it. You'll notice the difference. It requires this. So if I said, for instance, C++ sometimes, I don't know, man. Bird equals new bird. Okay, that works. I have no brackets here. C++ doesn't care. Actually, if I put brackets, okay, it's fine with that. Yeah, so in some places it's ambiguous, or some places it's fine with either. In some places, it enforces it. So if I, for instance, declared bird, and I did that, well, now the compiler is confused because it thinks I'm forward referencing this function, this bird function, right? It thinks this is a function that returns a bird. Or more accurately, it really can't tell. So if I declare a bird statically like this, I have to leave the brackets off. If I throw the bird like this, I have to put the brackets on, even though there's no arguments in either case. And if I take them off here, then it complains that a type name is not allowed. So yeah, C++, it's some of the choices they made, or some of the choices, I guess, that they got stuck with, really can really trip you up if you're not used to the language. But yeah, so that's why we throw a bird here directly. Yeah. What's that? Sorry. You could. You threw a pointer. I mean, that's, so you have to figure out what to do, right? If it's pointing to dynamically allocated memory and you throw it, then maybe you should. Yeah. So yeah, there's lots of options. Yeah, exactly. If I threw this bird, I could throw that. Now this is a dynamic piece of memory, but yeah, I don't know. Sure. Bird alert. No, it still catches it, but now I potentially have a memory leak. So yeah, that's a good point. If we're throwing statically allocated objects, everything's going to be okay. If we throw something that was dynamically allocated, maybe we have a problem. We don't delete. I would guess that you could. Let's try. It doesn't like that. Type name is not allowed. Okay, so I need to. So let's declare B. We can throw B. Yeah, it's okay with that. Can we catch B? I'm guessing yes. All right, so we got a bird alert. Yeah, so we can throw pointers as well. Whatever we like. Yeah, very, very flexible. Cool. Other questions? Okay. I think that was all that I wanted to look at here. Okay, so the order of the catch blocks matters. And here we sort of demonstrate. So if we have a class hierarchy where the base class is a vehicle, and then a car is a type of vehicle, and an aircraft is a type of vehicle, a boat is a type of vehicle, and a Mazda is a type of car. And we have a try block where we throw a car, and then we have all of these catch blocks. Well, this is not going to work very well because whatever we throw here, our car will be caught by the vehicle, right? Because our car is a vehicle, and then it's going to not get caught by this and not get caught by that, which is probably not the behavior that we want. So if we change this code a little bit and took out that catch block, now our catch blocks will work, nothing will get skipped, right? So the order of the catch blocks matters. We want higher in the hierarchy, we want the derived classes, right? So Mazda, we want before car. And if we wanted to catch a vehicle, it would be, if we wanted to catch a vehicle, yeah, the vehicle would be after Mazda and after car, right? So first we put our derived classes, then we put our base classes, and then if we want, at the end, we put the catch-all. We put the catch-all anywhere else, of course, we are going to have a bunch of useless catch blocks. All right. So as mentioned, we can also rethrow exceptions, right? So we have here our function. We have a try catch block. We have a dangerous piece of code. It calls this middle function. This middle function also has a try catch block. So we call this divides function. The divides throws this divided by 0. We can catch it, right? The same as we have the order of the catches. Well, there's an implicit order to the catches on our stack, on our function call stack, right? So it's going to look at the next function down to find a catch block. So it'll look at this catch block first. If this matches, it'll get caught there. And then what we can do is we can rethrow that parameter, right? So this allows us to do something like clean up in an intermediate function. Okay, so here we have, this is Timmy. Again, Timmy's in trouble. But we have a some name variable, and inside of our try block, we call enter name. So we want to get some user input, and then we potentially, something goes wrong. In our enter name, we call check name, and then check name throws some error if it figures out that Timmy is the name. Okay, so we'll just run that really quickly, and then we will put our intermediate catch block. Where are we? P6. All right, so that works. Timmy, main function says, help, Timmy's been kidnapped by a giant squid. Yeah. Okay. So now what we're going to do is we're going to say, well, maybe we have some cleanup to do here. Maybe we want to do something like maybe we want to get this string back to the calling function. We might think about maybe we could throw it. Probably not a great idea. We will look at those kind of solutions. Caught in, this is called enter name. Okay, so we caught an error here, and then we can simply, once we're done cleaning up, we can say, well, this is not really our error. I'm just going to rethrow it. So I can just call throw with no parameters. I can throw the error specifically, but yeah, let's see what happens here. Enter a name, Timmy. So Timmy, we throw this exception. The exception is caught in enter name. We do some cleanup, and then flow resumes in the main function because I rethrow this error. And Timmy's been kidnapped by a giant squid. Wouldn't you know it? So yeah, this is one way to handle if I have sort of dangling resources in my function that I know I need to clean up, and I know that I might have some error thrown up the function call stack somewhere. Then I can surround that in a try catch and make sure that I clean up whatever I'm supposed to clean up. All right. This is, I can also do this. with no parameter. And again, I caught it in enter name, I rethrow it, and then here it says help, Timmy's been kidnapped by a giant squid in the main function. So we're throwing the original parameter. I could also throw Timmy was eaten. Call off the search. All right, so I can throw something different than was originally thrown to me instead of, I can catch it, keep it, and just throw something new. The main function says Timmy was eaten, call off the search, and we still get caught by enter name. Okay, so these are quite flexible. Again, another thing we can do is we can use our catch-all, and then we don't know what we caught, so we can't use it, but I can rethrow it, right? So I don't know what it is, but the runtime system still knows what it is. The only reason I can't use it is because the compiler can't verify. But if I throw it, then it can still be caught up here. So right. So even though I caught something, I didn't know what it was, I can rethrow it and it can get caught somewhere else that actually knows, that's expecting it, and then it can get used up there. All right, so those are all the sort of, the intermediate try, catch, rethrow. Questions? All right, how are we doing? Okay, so this brings us to the point of this entire lecture. Oh, yes, we will talk briefly about this. So in C++, throw declarations are deprecated, right? So we used to use an earlier version of C++ where they were not, and then I think last semester I tried them again. It updated. So yeah, these are deprecated now. You can't use them, but you might see them, right? If you're working on an older code base, you might see something that looks like this. So when I declare a function and when I implement it, I can declare the things that function is allowed to throw. So in this case, my function func can throw an int or an exception. Anything else I would try to throw there, it would simply terminate, right? So this means that these are the only allowable things I can throw. It turns out, I guess, they weren't that useful because they stopped using them. So if I don't have any throws declaration, of course, I can throw whatever I like from this function. The only thing that I can do is I can throw and put the empty brackets. This is not deprecated, or at least, well, we'll see, I guess, today. It wasn't last time I checked. So if I put this, that means I can't throw anything. So any exception or error or anything that is thrown from inside of this function or any of its called functions will immediately terminate when it gets to this function. Right? So yeah, if anything is thrown from within here or within one of the functions it called terminate as throw. Yeah, let's try that down here. So here we could say, just for fun, let's give it a try. Well, it doesn't like that for a couple of reasons. It's going to let me do it. See if it compiles. So again, we have to have it on the declaration and the implementation. Let's see if that works, actually. Yeah, so we get an error. C++17 does not allow this type of thing, this type of nonsense. Okay, but what we can do is we can say, well, this function does not throw anything. And I believe, last I checked, that was still allowed. Yeah, so it gives a warning. This will always terminate, but it does not give me an error, so I can actually run this. Timmy, and then terminate is called right from the check name function. Okay. All right, again, you might see that in older code bases, but any questions? All right. All right, so stack unwinding, we've talked an awful lot about it, right? If I throw something at the top of a function call stack and the catch is, 3, 4, 8 functions down, it's going to pop off all of those stack frames until it finds the proper catch block. So it bypasses this normal return structure, and we've seen repeatedly how code can get skipped. But the main problems are things that I've allocated, right? So resources that I've grabbed a hold of and maybe not released, right? So the most common, I guess, or what you might be the most familiar with is dynamic memory. So if I called new in this function and I did not get a chance to call delete, that's potentially a problem. But I can also have open files or things like that. Certainly, return values will not be returned, so that will cause a problem. So when we throw something, we can reach this sort of inconsistent state. I don't know if you've ever, I have for fun put this line of code in things that I've written, and then had it execute. So yeah, I wasn't as smart as I thought when I put it in there. But I mean, one of the reasons that can happen is if I throw an exception, well, that's an abnormal flow of control of your program, right? It's something that's a little unexpected. So that wasn't the case when I did it, but so yeah, we might have intermediate functions with allocated resources, and we want to clean them up. So we're going to look at 3 possible solutions: 1 bad, 1 good, and the best one, which is we'll talk about when we get there. So 1 is I can, whatever I'm throwing, whatever I need cleaned up, I can throw it, or I can throw some sort of error that contains it, catch it, delete it in my catch block, and print an error message. The problem is, well, first of all, this violates encapsulation. Right now, the catch block has to be aware of how the code is being executed down the function call stack. That's bad, because I might change it. Also, are you sure somebody's going to delete that for you? Well, you better be sure. The other potential solution is I'm going to put a catch block. So if I have an intermediate function that I know has open resources, I'm going to put a try around the dangerous stuff and put a catch block, and that catch block will close the resources. So this is good. Each function does its own cleanup. That's good encapsulation. You don't need to know particularly what's happening further up the call stack. All you need to know is something was thrown. You do your business, you rethrow the exception, and that's good. The other is this make everything an object. It's called I think it's called this. Resource acquisition is initialization. So every time I open a resource, I tie that to the lifetime of an object which is statically allocated and will at some point have that lifetime expire, right? So this is a very sort of safe way to manage your memory, where everything is going to get handled by basically being popped off the stack. So when we do that, the cleanup is automatic, as long as we implement the destructors properly. So let's take a look at these 3 possible solutions. Okay. All right, so here I have a class called error. It's a friend of the main function. Why did I do that again? Oh, yes, because I want the main function to be able to handle these resources. So basically what's happening here is we call initialize. In initialize, I'm going to ask the user for the number of elements. I'm going to take that input, and I'm going to make a dynamically allocated array on the heap. All right. Incidentally, why don't I do this? Right? So this is a little bit weird, right? I'm taking in a dynamic value, a size, and then I'm allocating an array of unknown size on the function call stack. So C++ will let you do this. It's not necessarily a good idea, right? So I have my function call stack. Presently, it takes up this much memory. If I statically allocate an array like that, it's going to grab however much more it needs. It'll still run. The problem is, what if I put 1 billion, right? What if the user puts 1 billion and then I run this code? I can get a stack overflow. So generally speaking, it's safer to put that on the heap. The heap can always grab more memory. The stack will run out. So yeah, this is, if I want a new array that's local, well, pointer will be local. I'm going to put it on the heap. It's safer. And then once I enter the size, I'm going to enter all of the elements. I'm simply going to read them into this array of integers. We can check if the input is good. And then we're going to print out all of those numbers, and then we're going to delete that array. Okay, so let's do all of that. Oops. Array 3. Okay, well, oh yeah, I made some changes. That's fine. I'll fix it later. Okay, so array 1, enter the number of elements, let's say 3. Enter the elements 1, 2, 3, and it says you entered 1, 2, 3. We have no memory leaks. That's fine. Now, if I enter something other than an integer, then I'm going to flip this flag and throw this error. And now this won't get deleted. I'll get caught here, and I'll have a memory leak. So if I do let's put 2 elements, 1 and 2. In this case, all heap blocks were freed, no leaks were possible. 2, A and B. Now we have a memory leak because we bypassed that. So what we're going to do is we're going to change this to hold an int to delete, and we will put that in the yes, BD. Okay. All right. And then here we will simply delete it. Right. The main function is a friend. Okay. And then down here we say error bad input, but we're also going to pass in my array. Okay. So now we should have some memory safe code. Yeah, that's fine. So number of elements, let's put 3 and A, B, and C. And yeah, we've cleaned it all up. We've violated a lot of principles of object-oriented programming and encapsulation, right? Because now this class needs to know how this function operates. And if I change how this function operates, stuck, right? I have to go in and change this class. And I also have to change this other function. So if I make 1 change, I have to make 3 changes. This is a bad design, but it will work in this particular situation. Questions? 5 minutes, all right. So the other one is we have the same thing here. What were we gonna do? So enter int. We're gonna call a function now that takes some input and then possibly throws an error. So this for loop might throw an error. So we're going to put this in a try catch. I'm going to use some bad form here. I don't care what the error is. I just need to delete my array. Okay. So yeah, if we run this, yes, I know. Number of elements 2, A and B. All right, double free. Goodness gracious, what did I do? Oh yeah, this is an array. I always seem to do that. And we want to run this with Valgrind as well. Block was allocated. Did I do something I didn't like? Well, regardless, we have no memory leaks, so that was sort of the purpose of that. Sure, just a second. I forgot to rethrow my error. Oh, did I run make? No. A and B. Okay, that looks better. Error bad input. So that executed, but we freed up our memory by catching it in our intermediate block. So yeah, that's solution number 2. It's a good one. Doesn't violate encapsulation. This function handles all of its own cleanup, and it doesn't need to know how other functions operate. Questions? All right, the final one, we have 4 minutes left. So this is so what we're going to do now, we have, instead of a raw array, we're going to use an int array. And what you would use is a vector, right? A vector is going to clean itself up. But if we were stubborn and we really wanted to use our own class, well, we could initialize size, size equals s, and pointer equals new int s. Okay, so our int array now is going to hold the pointer for us, and the other thing it's going to do is delete it for us. And we have a subscript operator, so we can just overload that. We simply return by reference pointer at index. Okay, so now we have this class int array that's going to behave a lot like an int array, basically, except it's going to delete itself if it goes out of scope. Okay, so now in my initialize function, instead of a raw array, I make an int array. A couple things that are nice is that the backing array is on the heap where it should be, but I don't have to do that myself. That's handled in the class. And then I can take all of this input. Possibly I throw this bad input, right? So here, we'll get to that. I don't know if we have time to get to that. Okay, so now my array 3 works. If I have 3 elements and say 1, 2, 3, that works. If I say 2 and A and B, I get this bad input error. And let's check with Valgrind. Right, and then I don't have to catch this error in my intermediate function, right? Because when that stack frame is popped off, all the local variables are destroyed, which means their destructors are called. So the destructor of my int array is called, and this, geez, I can't even believe that worked. I always forget that, apparently. But it's C++, so sometimes your mistakes work. But yeah, so this object, which I declare locally now, gets deleted automatically. The destructor is called and my dynamic memory is destroyed. So that is this resource allocation is initialization, where you tie the life of any resource that you open that you're not necessarily sure is going to be closed or deleted. You tie it to the lifetime of an object, and then you will never have resource leaks unless you have object leaks, of course, but that's the idea behind it. So yeah, questions? All right, so that's it for today. What is today, Wednesday? I guess I will see you guys next week. So get your tutorials in, and please, try to have your assignment 4 done by Wednesday. There's a possibility that's extended, but it's not guaranteed. So yeah.